Okay, in this section, we are going to look at the example involving our definition of current, resistance, and also our Ohm's law. But before we delve into that, it's good we remind ourselves that if we have to, we have several ways of connecting our resistor. This is a symbol of a resistance. So we have a resistor, resistor 1, resistor 2 connected in series. This is R1, R2, R3. If we have them connected in series this way, the overall resistance, that is the equivalent resistance of this three, is going to be R1 plus R2 plus R3. Okay, this is the R equivalent of the R1, R2, R3 in series. Well, when we have them connected in parallel, let's say we have them connected in parallel here. We have them here connected in parallel. If we have them connected in parallel this way, then the overall resistance appearing at these two terminals is going to be given by the expression. So R equivalent in this case, R equivalent is going to be obtained from 1 over R equivalent equals to 1 over R1 plus 1 over R2 plus 1 over R3. So you have to evaluate this expression and also solve for the R equivalent. Okay, this is for parallel connection and this is for the series connection. So with this information, we can try to attempt additional questions under current, resistance, and Ohm's law. Okay, here is a question that relates the definition of current and other parameters of our conductors. In this question, it is good, as usual, to copy the question down and force the video, attempt the question so that when we attempt it collectively, you can realize some of the mistakes you might have made in your own attempt. That will help you very well. So let's look at the question together. We are told that we have a copper printed circuit board and there is a pass which has the following dimension, that the length of the pass is 3 centimeters, the width of the pass is 4 millimeters, and the thickness of the pass is 0.1 millimeter. And this pass is carrying a current of 100 milliamp, and the question is to evaluate the drift velocity of the electrons that is moving along the track. So if you could recall, we have a formula relating the current, the density of the charge carriers in a given conductor, the area of the fast, and the drift velocity of the charge carriers when they are accelerated along a particular section of the conductor. So our density, that is the charge carrier density for the copper material, is given as 8.49 times 10 to the power 28 number of charge carriers. In our case here, number of electrons in 1 cubic meter. So if we can sketch the track here, this is a track in an exaggerated form. This is a track, and the track is having a rectangular face here. This is rectangular. The length of the track is given as 3 centimeters, and the thickness here is 0.1 millimeter, and the width of the fast is 4.0 millimeter. So if we can write our relation for the current through the conductor in terms of the other parameters, we say current is always the the charge carrier density, the charge on the charge carrier, the drip velocity, and the cross-sectional area of the conductor. This is the formula we discussed we derived last week. So from here, our concern is to evaluate the drip velocity. So we can make the velocity the subject of the formula here by dividing both sides by the coefficients of the velocity. If we do that successfully, we are going to get the drip velocity to be evaluated from the current divided by the charge carrier density, the charge on the electron, and the cross-sectional area. So this current is given to us. Let's substitute these values into our expressions. So our drip velocity will be, instead of our current, we put our values here, 100 times 10 to the power minus 3, so that it is in ampere, not milliamp. All of our charge carrier density is here given in the information the question carries, which is 8.49 times 10 to the power 28 per meter cube, times the charge on electron is 1.6 times 10 to the power minus 19 coulomb. Here we are after the magnitude, so there is no need of the negative sign. Multiply by the cross-sectional area. The cross-sectional area is our length, our width times the thickness here. The length is not participating in the cross-sectional area. So this is going to be our 4 times 10 to the power minus 3 meter, that is the width, multiplied by the length or the thickness, which is 0.1 times 10 to the power minus 3 meter. Evaluating this will give you, plug in those values correctly, you are going to get the velocity of the electron in the copper as 1.84 times 10 to the power minus 5 meters per second. Very, very slow velocity. Okay, so let's try another question. Here is another question which also involves copper wire here. We have also a copper wire, and it carries some current, and we have the cross-sectional area of the wire to be 1 millimeter square. The length of the wire is 6 meters long, and it is assumed it is carrying a current of 2 ampere. Okay, so the question is we are to estimate the time it will take electron to move from one end of the wire to the other end. Okay, so let's say this is the length of the wire. Okay, and we have the switch somewhere here which will switch on this is one end of the wire, and let's imply that the distance from here to here is 6 meters. Then the wire is so small such that the cross-sectional area of the wire A is 1 millimeter square. Okay, we are told also it is a copper, so it is indirectly we are going to assume that the current, the charge carrier density is as in the previous question of 8.49 times 10 to the power 28 per meter cube. Okay, so when we write our formula here for the current is going to be given by this expression, where N is the charge carrier density, E is the charge on the charge carrier, and B is the drip velocity, and well, A is the cross-sectional area of the wire. So in this case, we are asked to evaluate time. Okay, so we can use an expression that relate time and the distance. The length of the wire is the distance the electron will cover from this end to this end, and this distance can be evaluated from the product of the speed of the charge carrier times the time it takes for the electron from one end to another end. This implies that our velocity can be evaluated from the ratio of our velocity can be evaluated from the ratio of the distance over time, so that our new expression here can be given in this form: the distance, the length of the wire over the time taken, multiplied by the area here. So in this case, we can make the t the subject of the formula, since we are looking for how long, so we are after time. So this t can come here, I can come here, so the time taken will be our charge carrier density, our charge on electron, the length of the wire, the cross-sectional area, all over the current the wire is carrying. So virtually all the parameters in the numerator and denominator are given in the question. Our current I is given as 2 amperes. Our charge carrier density is given in the previous question. Charge on electron is known, 1.6 times 10 to the power minus 19. D is the length, the distance traveled by the electron from one end to another, and that is equivalent to our 6 meters. A is the cross-sectional area, which is also given in the question. So let's plug in this and evaluate the period at the time. N is 8.49 times 10 to the power 28 times E is 1.6 times 10 to the power minus 19 times the area there is going to be 10 to the power minus 6 meters square, multiplied by the distance, which is 6 meters, all over our total current 2. If you evaluate this time correctly, you are going to get something like, so the time it will take electron to cover this distance of 6 meters is evaluated to be 4,752 seconds, and this is equivalent to how many hours? This is around 11 hours 19.2 minutes. Okay, so this is a period it will take very small velocity, where that means long time. The electron is going to take 11 hours before the electron of this end move to this end. What is the implication of this answer? We are coming. Let's attempt additional here is another question involving charge carrier density, current, length, of some dimension of the conductor. In this question, we are given that we have two types of material. We have silicon and metal. Okay, and it is known that silicon is a semiconductor material, and it has fewer charge carrier per unit volume than the metal. Then we have a piece of copper, which we have been using since the in the previous two questions. We have a silicon, and this silicon have the same dimension with the semiconductor, and the current with the copper. The copper has the same dimension with the semiconductor, with the silicon, and they all carry the same amount of current. So we are given that the drift velocity in copper is 2 times 10 to the power minus 5. And the question is, what is the drift velocity in the silicon? Making use of the expression that current is always here. So we have to evaluate current in copper and current in the silicon. But from this expression and looking at our our data, we can see that our data is relating our current with the dimension of the such that if we evaluate the current over the dimension, the area, this is equivalent to N if where V is the drip velocity. So evaluating this amount for copper, let's say for copper we put C here, the cross-sectional area for copper, the charge density for copper, charge carrier in the copper is electron, and this is the drip velocity in copper. Okay, similarly we can express this for the silicon, the cross-sectional area of the silicon, and this is the same as the charge carrier density of the silicon. Electron is the same electron. Drip velocity is the drip velocity of silicon. So if we go back to the question says that the silicon and the copper have exactly the same dimension and carrying the same amount of current. Dimension and current having the same implies that our ratio, the current density, is the same as in copper is the same as the current density in the silicon. Therefore, we can now equate our two relations. The charge carrier density in copper multiplied by the electron times the drip velocity in copper is equivalent to the charge carrier density in silicon times the electron times the drip velocity of the electron in the silicon. It is easy to see that the charge on the electron cancel, and we try to make the drip velocity in the silicon the subject of the formula, so that the drip velocity in silicon is going to be the charge carrier density in copper over charge carrier density in silicon multiplied by the drip velocity in copper. So doing this successfully will give us the NC is 8.49 times 10 to the power 28. That is the one given in the free. I think we need to correct this one. This one is not correct. This is the correct value over this density of silicon, which is 3 times 10 to the power 18. Okay, times the velocity in copper is how much? Velocity in copper is 2 times 10 to the power minus 5. When you evaluate this correctly, you will have the drip velocity to be okay. When you evaluate this value correctly, you are going to obtain 5.66 times 10 to the power 5 meter per second. You can easily see that this speed is much higher than the speed of electron in the metal. In the metal, the power here is minus 5. Here it is times 5, which is of the order of 10 to the power 10, the difference. Okay, these are the questions we can attempt in the for us to know how to make use of this formula of the current. The implication of this low speed and the fact that our speech is